All set to go? Yeah? Okay. Hey everyone, thanks for coming to my talk. Today we're going to be going through navigating the machine learning landscape for Apple. My name is Meghan Kane, and I'm a developer at Novoda. It's an app consultancy based in Berlin. And my Twitter handle is Megaphone, if you want to follow me. So we've all heard the excitement about how Apple continues to provide us with machine learning offerings. And this is a great opportunity for people to get started with using machine learning in their apps, even if you don't have any experience at all. But while this can be exciting that there are so many opportunities, it can also be confusing to know how to get started since there are so many options to choose from. And this keeps growing each year. So in order to navigate ourselves in the Apple machine learning landscape, what better way to do this than to take a road trip? So let's make a tour itinerary. First, we're going to go through when to use machine learning in your apps. Probably a bunch of you are familiar with this, but we'll just do this so that everyone's on the same page. Next, we'll look at what role does mobile, specifically iOS, because we're looking at only Apple products, have in machine learning. Then we'll look at what tools do we have, which ones should be used for what purpose, and we'll also go through 2 machine learning examples. So when should you use machine learning in your apps? We should definitely assess this beforehand so we don't use machine learning when we don't actually need it. So this isn't an exhaustive list, but these are some tasks that are suitable for machine learning. So if any of your apps have any of these tasks, then maybe you consider machine learning as an option. So if your apps are trying to do any detection of faces, rectangles, or text, or if they are doing any classification of images, text, or activities, so that would be like detecting if a user is walking or running or doing any sort of custom activity. If your apps are doing any sort of regression, so this is pretty broad, but as a general overview, you can think of it as predicting any value from any sort of independent variables. We'll go into it a little bit more later. Natural language processing, so this is extracting meaning from any text, or style transfer. So this is when you take one of your photos and you apply an artistic style to it. So probably a lot of you have seen changing your photos to look like they're in Starry Night style. So when we talk about using machine learning in your apps, let's be more concrete about what we're talking about and which parts of the machine learning process this mostly takes place on. So for machine learning, there are 2 main stages. There's training, and then there's inference. So training is the process where the learning in machine learning really takes place. For now, let's think of training as the process of producing a model by learning from a lot of data. We'll go into it a little bit more detail later. After training, we evaluate our model to check if it makes predictions for whatever task you're performing that are accurate enough. If the accuracy is high, we are done, and our training process produces our model. If not, sometimes we have to repeat this process and collect more data and do the training and evaluation process over again. At the end, when you're satisfied with its accuracy, then the model will be produced, and then you can make predictions with it for whatever task you're trying to perform. So when we have that model, then we move to the inference part. And inference is just a fancy word for prediction. So don't get tripped up by that. So where are training and inference being done when we're talking about iOS? Training is still computationally expensive, relatively, even though the devices are getting a lot more powerful. But for the moment, it's still taking place on the server on your laptop. Traditionally, inference would also be done on the server. That was happening for quite a while, and you can still do this. A way of doing this would just be a very standard setup where you have the back end of your app hosting your model, and then you make a network call from your app to get a prediction. However, when we're talking about machine learning for iOS, then we're talking about doing inference on the device. So that's what they really mean. It's taking a pre-trained model that you've already gotten from the training process and hosting it on your iPhone. That way you can make you can make predictions locally on your device without having to make a network call. So what are the advantages of doing inference? The main ones are that you have user privacy benefits. So the data that's passed into the machine learning model that's being hosted on the device is kept local, so you don't have to send it to the server. This leaves users with perhaps a bit more trust. And then you have the low latency experience. So this comes from the fact that you don't have to send the network calls to make predictions. So this is particularly helpful if you think your users won't have that strong of a connection, or if you're trying to perform many predictions in a short period of time. So if we go back and look at that suite of Apple machine learning related offerings that I showed before, so we have Vision, CreateML, CoreML, Turi Create. Maybe some of you have heard about some of these or used some of these in your app so far. We also have like CoreML tools though, and Gameplay Kit, NLP, and Metal. The list goes on, and I'm actually not including everything that has something to do with machine learning. So how can we put these in terms of those training and inference processes that I just talked about? So CreateML, Turi Create, and Metal would go in the training part. And then in the inference, you would have natural language processing, Vision, Gameplay Kit, CoreML, and also Metal. In between, you have CoreML tools, which was doing a conversion of a pre-trained model from some other platform, such as Keras or Cafe format, and this was converting it into a format that's understandable for CoreML. So we only have 45 minutes on our road trip, so we're not going to focus on all of these. So we're just going to focus on CreateML, Turi Create, Vision, and CoreML. So in terms of specific formats for Apple, CreateML and Turi Create, when they're done training, they produce a model that's in ML model format. So this can be dragged and dropped into Xcode, and Xcode simply auto-generates a Swift file from the ML model. And then when the model can be used with the CoreML framework seamlessly to perform inference or make predictions, as I said. So you might be wondering what happened to Vision. I thought we were supposed to go there on a road trip. Well, I put it off to the side because Vision's even simpler to use. You don't actually need an ML model at all. So this is already built into the operating system, so you can just use the framework directly. So if you want to do something like face detection or rectangle detection, then you don't actually have to work with a model. You can just make calls directly to the Vision framework. We're going to go through the capabilities of each of these later, too. So, OK, our road trip stops are Vision, CreateML, CoreML, and Turi Create. So as you do for road trips, let's make a bucket list, too. So probably the first thing on your list when you're going on a road trip would be to make iOS apps that are using machine learning. So the first thing that we'll put on our bucket list is we want to make an app called Instruction Buddy. And this is going to interactively help you learn the rules of board games. So maybe I like board games, but sometimes people don't want to learn a huge set of rules. And so this will put the instruction manual into the app, and it will also allow you to classify board game pieces when you take a photo of it. So you don't have to keep going back and searching through the big instruction manual. So the game I use is Agricola. And the second item on our bucket list is going to be scrapbook. So this is going to take memories from our road trip, and for the photos, we want to be able to transform those photos into a style of an artistic painting. So we're going to be using style transfer for this. OK, so let's get started with Instruction Buddy. So we're going to be classifying Agricola board game pieces. So I didn't show this in the diagram before, but the first thing would be to properly frame our problem before we do the training process and then the inference part. OK, so we're trying to classify these Agricola board game pieces, and we're going to have 5 of them that we're able to classify. So we're going to build a classifier that's able to take an image of an image and then classify it into one of these 5 categories or classes. If the user takes a photo of something else, then it's going to be classifying it as one of these. So that's something that we'll talk about handling a little bit later. So the machine learning approach would actually be to first try to constrain the environment as much as possible so that you don't have to collect data from a lot of different environments, and you have a higher probability of knowing what's going to be passed as an input to your model. So in order to do this, I thought an easy way would be that you ask them to put the board game piece in the box of the game. This is totally acceptable to do also, and it makes the user experience a lot better if you're able to do this. So first, let's try to detect that game box, because we want to put the board game piece in there. And then we want to classify the Agricola piece. So I just mentioned it, but why would you detect the rectangle first? Restricting the input is going to be a very quick win to boost the model accuracy. And then additionally, it's going to be faster to collect the image data so that you can just take images that are restrained to that box. Also, data collection is usually one of the more laborious parts of machine learning. It's oftentimes not the algorithm portion. It's collecting the data. So this is something you really want to keep in mind. OK, so let's first stop at vision, and let's see what this framework has to offer for us. So vision has been around since iOS 11. And so what we're able to do since it was released is we can do face detection, facial landmark detection, rectangle detection, barcode detection, image alignment. So if you have a bunch of images, then it's going to try to align them so they look like they're stitched together, and text detection, and object tracking. So this is perfect. We want to detect that box, so we can use the rectangle detection API from the vision framework. So since the last step that we left off at was framing the problem, normally in machine learning, you would go through, pass through the training portion of it, but we don't have to do that because we're just using the vision framework, and it already has the model baked into the operating system for us. So we can just bypass that whole middle part and just go straight to predicting. So how do we create a request to do rectangle detection in vision? So it's very simple and straightforward, and there are 4 main steps to it. So first, we're going to create the vision handler. And then we're going to create a task-specific request. And then we're going to send the request to the handler. And then finally, we're going to handle the results. So what does this look like? So yeah, we create this handler, and it's a VN image request handler. And it takes in the image as the input, as the CG image, and then also the orientation. It's important that you do pass in the orientation because it doesn't work as accurately if you have it like rotated by 180 degrees, for example. The next step is creating this task-specific request. So all you need to do is create the request in vision that is relevant to whatever task you're trying to do. So we're trying to detect the box, which is the rectangle detection. So we create a VN detect rectangles request. If you're trying to detect faces or something else in vision, there's an analogous request for each of those. We have to give it also the completion handler, so it knows what to call when we get the request back. So now we have to send the request to the handler. This is just calling perform on the handler with the request that we just created. It can take an array of requests, but in our case, we just want to make one. And lastly, we want to handle the results. So handling the results, it comes back as a optional request object as an array of VN rectangle observations. And we want to do something with these. And this is going to be bounding box coordinates of the rectangle that it detected. So perhaps you want to, for this, we're going to want to crop it out. And then we're going to want to send it into a model for classifying that piece. OK, so we were able to finish the first part of our machine learning approach, which is detecting the rectangle. Next, we have to classify the Agricola piece. So for this, we're going to need a custom image classifier. And we weren't able to find that in the vision framework, so we're going to have to look elsewhere. So let's see if it's going to be in the next stop of our road trip. Next, we're going to stop at CoreML. So CoreML, what does it offer for us? This is the new framework that was just introduced in iOS 12. So this is the first time we're able to train machine learning models completely in Swift. Before, you had to train models in an external framework, and those were mostly written in Python or languages outside of the Apple ecosystem. So this is a big step forward. So it allows us to train custom models for a couple of different tasks. So the first one is image classification. So this is going to be what we want to use to classify our Agricola pieces. we're also able to do text classification and column data classification and regression. So what does that mean, though, column data classification and regression? So you can think of an example of this as being, so it can take an input of CSV as a CSV, and this could be values for example, if you wanted to predict what kind of wine you have based off of values that you have about the wine's acidity, alcohol content, color intensity, and a couple of other characteristics. This would be an example of column data classification. This is actually an open data set that's available online, so that's why I mentioned it as an example. For regression, you can think about any problem where you're trying to find a relationship that models like one variable with several others and actually gives you a value, not a classification. So an example would be if you're trying to predict the price of houses in a region with features such as the number of bedrooms and proximity to public transit. So since this is within the Apple ecosystem, we can do this all on Xcode Playgrounds, which is awesome. So let's see how we can get started with this process, though. We can't just jump directly to Xcode Playground and create our model with CoreML. We actually need to collect the data first. So how are we going to do this? So we can follow some guidelines that are general for doing any data collection. So the main goal that you want to have in mind when you're collecting data should be that you want to collect data that's going to enable you to create a model that will generalize to the real world. Because even if your training accuracy is really high, it doesn't really matter very much if it's not able to generalize to what your user uses in the wild. So in order to be able to generalize to the real world, we want to follow a couple of these steps. So first, we want to collect images representative of real-world use cases. So this involves trying to imagine yourself in these situations that a user could possibly be in. Next, we want to vary the angles and the lighting of the images because, for example, for the board game pieces, the user might be taking a photo directly above it, or they might be taking it slightly sideways. They also might be in a very well-lit room, or they might be in almost darkness. And this will really affect the ability to make an accurate model. Apple recommends that you use 10 images per label or per class, but ideally you should use more because this is really tough to generalize if you have such a small data set. So this would be the absolute bare minimum. You need to have an equal number of images for each of these labels too. So this is really important. So it won't really suffice if you collect 1,000 images for one category and then 15 for the other. It's like you can't average them out and say, oh, I have like this many images per label in average. You need to make sure that you have an equal distribution for these. They also recommend that you have at least a 299 by 299 pixel image. So what does the real world look like? This is going to depend on your use case, but for us, we're just trying to classify this board game piece, and it's just in the inside of that box. So it makes it very easy for us because we know that they're going to be taking the photo inside of that box, or with the inside of that box. If they don't, then they shouldn't really expect to have a prediction. So if they point the camera at a copy machine and it predicts one of the values of the pieces, then they kind of should expect this because they were supposed to point it at the inside of the box. So we can collect this data pretty quickly because we have a really restrained world that the user is supposed to be in. And the way that we can do this is we can, instead of taking a lot of photos of the different board game pieces inside of the box with different lighting conditions and angles, we can actually take videos for each of the situations that we think the user should be in. So we can go through all those guidelines and take a video for each lighting condition and each angle for each of the board game pieces. And it really just has to be a minute long or even less, as long as you're able to cover all of these conditions in that time period. And then from there, you can take the video and you can extract the JPEG frames from it using a tool called FFmpeg. If you don't have FFmpeg, then you can easily install it with Homebrew. And FFmpeg expects you to input the movie file of the video, And then it also expects you to input the frames per second. So although the frame rate's really high for videos taken on newer iPhones, you want to keep the frame rate low for extracting images out, because if it's too high, then you won't actually have really unique images. It will be as if like you're having almost duplicates of a lot of these images, so you want to set this low so it waits to extract the frame at a slower rate. So by doing this with videos, you can cut down a ton of time. So once you have that data, then you need to prepare it so it's able to be used with CreateML. So a recommendation, a rule of thumb, even outside of CreateML, is to first try with 80% of your data in the training set and 20% in a test set. And the way that CreateML is going to expect this, though, is simply in 2 different folders, one for training and one for test. And then you're going to have folders for each of the categories of what you're trying to predict. So you can see for the training data set, we have a border, which is one of the pieces, a feeding trough, a reed, a stone, and a wood. We have the exact same subfolders for the test folder, and this is really important that the labels are consistent. Okay, so we're ready to train. So as I said, we can use this CreateML right inside Xcode Playgrounds. And there are 2 different ways for doing this. You can do this using a live view, which I'll show, or you can use a Swift script. So if you're using the live view, then you're going to have to import CreateML UI framework. And then all you have to do, it's just these 2 lines of code, is you need to create a builder, which is an ML image classifier builder. And then you just need to call show in live view on that builder. When you open up the live view, you're going to see the name of your classifier, and then you're going to see a prompt to drop the images in from the training set in order to start training the model. So we'll take that training folder that you just saw in my Finder, and we drop that in, and then it's going to start training. So it processes all the images first, and then it's going to start training, going through different training iterations, and you'll see how the accuracy should improve over time because it's coming up with a model based off of the data that's sent in, and hopefully is improving through each of those iterations. So after that's done, we're going to be able to see the training and the validation accuracy. So validation data is set aside by the framework. It's separate from the test and the training data, and it basically acts as a testing set while you're training. The testing set is used after the model's finished training. You don't really have to worry about it so much, but I think it's interesting to know because it's one of the accuracy values that's given. Apple sets aside 5% of your training set for this validation set. So we got 100% accuracy on both training and validation. This would normally be a bit suspicious because it's too high, but our environment was constrained so much. It only is expecting these images inside of this box. And so there's really only so much variation there can be, and we have a much greater chance of having a higher accuracy because of this. So in the debug output, that's where you can see the different iterations that the training process is going through, how much time each of these is taking, and the training accuracy and the validation accuracy. So yeah, this took less than a minute, and the training accuracy was 77% accurate at first, and it went all the way up to 100% by the 10th iteration. The validation accuracy was increasing at a very similar rate, and you should hopefully see these moving in parallel. If the training accuracy was trending in the right direction, but it wasn't very accurate at the end of training, then we might want to increase the number of iterations. And we could do that in the live view. There's a toggle where you can put the number of iterations to whatever number that you want, just that the default is 10. If the validation accuracy was very low compared to the training accuracy, or it was like fluctuating, trending in the right direction, then it was going backwards, then this is a red flag that we probably need more data. So in our case, it worked very nicely, but I think this is really good to know because this is something you'll inevitably come across if you're training a custom model. So next we want to evaluate this model. So this is when we take our test data that we had set aside as 20% of our total data, and this is when we are going to pass this into the model in order to get predictions on the model that we trained. So we can see several helpful metrics that give us insight into the quality of our model. So our model predicted correctly 96% of the time on the test data, and this is the most obvious metric to look at, but we also should look at the precision and recall that we have. So our accuracy was very high, and so we don't have so much to worry about. We can be pretty confident that our model generalizes well to data you might see in the wild, but we can use precision and recall in order to try to tell if it wasn't the case, where did we go wrong? So precision and recall were printed in the debug output, and precision describes how effective the model was at applying a label only when appropriate for a given category. So if it was 100%, then the model predictions had no false positives. So we can see that that's actually the case for border and feeding trough. The recall, on the other hand, describes how effective the model was at finding all the relevant examples of a category and discovers false negatives. So if the recall is 100%, then the model predictions had no false negatives. If it's lower, then it had some false negatives. So we can see that the model predicted false positives for both reed, stone, and wood, and it predicted false negatives for both stone and wood. So you could use these as proxies into like how you should change the data and add more, and when it's overestimating values for certain categories and underestimating for others. Okay, so how is this so fast? This only took a minute. A lot of people have probably heard that you need a lot of compute power, a lot of time, and a lot of data. We didn't need any of these for this. So we should probably take a look into why this is happening, because it can yield some insights into how this is possible and like what technique Apple is using under the hood. So it's using something called transfer learning, and in order to explain this, I need to go through a little bit about what the type of network is being used for CreateML, for image classification. So for this image classification task, we're using a deep neural network, and so that just means we have a neural network with many layers. And the image input is represented as a large matrix of the image's pixel values. So this example is for a car, and so this car original image would be transformed into its pixel representation. And then it's passed through each of these layers, and those layers act as a transformation on the input matrix. And at the end, you have an output, and this is a probability distribution of what it thinks the input image was. So for this example, we would want the highest probability for it to be an Audi A7, since that's what was passed in. And for our specific example, we would want it to output whatever board game piece we were inputting. So this process of training updates the weights at each of the layers of the network. So the series of transformations at each layer over time will be more accurate. And back in the day, people used to train all of these layers, and that's called training it from scratch, and that used to take a lot of time and compute power and a lot of data. But if we look at the illustration of what's being done or what the network sees at each of these layers, we can start to see why we don't really need to train this from scratch like people used to. So if you look at the beginning, you can see that each of the layers that are closer to the input are detecting very generic features, such as lines and edges and gradients. In the later layers, it's not until then until we're detecting more specific features. So if some of these layers that detect very generic features are applicable to cars and like a lot of everyday objects, then shouldn't we be able to reuse them for classifying other image data sets? And yeah, that's exactly the case, and that's what transfer learning is doing. So it's reusing a lot of the layers that are in the beginning in order to transfer the knowledge that it learned from that network into creating a new network with your custom data set. So in CoreML's case, it's just training the last layer of the network. So that's why it takes such a short period of time and doesn't take much data at all. So this is a huge leap forward. And a lot of people are predicting that a lot of gains in machine learning applications come from this transfer learning technique because it frees a lot of people from these constraints that they were held to before. So we have the model now to make predictions. So we want to actually make these predictions in your apps. So how do we do this? So we're going to have to go to our next stop in the tour. So CoreML. What are CoreML's capabilities? It can perform predictions using a model, which is exactly what we're going to do. We're not going to be able to go through the rest of these, but I wanted to mention it. It's also able to quantize the weights in the model. So each of these layers that we saw in the network, it has weights associated with it, which is part of what's happening when you're doing the transformation. It's it's doing calculations with these weights. And so these weights by default were 32-bit, but these can now be quantized to lower amounts. So 16-bit or 8-bit or 4-bit, all the way down to 1-bit. And so this can severely decrease the size of your model. It can also perform batch predictions now. So instead of just performing one prediction, you can batch them together. And then you can also create custom model layers. So in the past, CoreML didn't support every layer that could come from a trained model that you trained elsewhere, and now it supports any kind of layer. So now we want to predict. How are we going to do this? So since we are doing an image classifier, we can actually use CoreML with vision. So there's a special CoreML model called a VN CoreML model. And we want to use this because if you're working with images, CoreML itself will make you work with CV pixel buffers, whereas a Vision CoreML model will allow you to work with CG images. So this is easier to work with, so it's recommended to go this way. So the first thing you're going to do is create this Vision CoreML model. So first you create this model that's for CoreML, and it's going to be called Agricola Piece Classifier in our case, and this is just the Swift file that was generated from the ML model that we got from CreateML. So it was auto-generated for us. Next, we're going to create the Vision CoreML model and pass in that CoreML model's model property. Next, after that, we're going to create a handler. So this is pretty much identical to the Vision process before. So we're going to create a handler, which is the VN image request handler, which passes in the image and the orientation. And then we're going to create a task-specific request with that Vision CoreML model and a completion handler when we get the results back. And we're going to perform the request on the handler, just like before, and we're going to handle the results. In this case, it's going to be classification results from our image classifier. So yeah, this is going to come back as a optional array of Vision classification observations, and we'd want to do something with the results. So maybe in our case, we want to show them that it detected a border piece and then tell the user what that piece is capable of doing in the game. So it helps them with gameplay. Cool, so we're done with our first bucket list item. So the next one we're going to move to is the scrapbook. So we want to transform photos to be in the style of an artistic painting. So perhaps you want to transform a photo of a city to be in the style of nice artwork. So you can actually use any style for this. You're not limited to Starry Night or ones that you have seen very famously online. You can pass any sort of artwork that you're able to find. So we haven't been able to do style transfer with any of the frameworks that we've seen so far, but let's take a look at what Turi Create can do. Turi Create is a Python framework, so we're not in the Apple ecosystem anymore, unfortunately. But you'll see how easy it is to use. You just need to be able to read Python and then write just a little bit of it. But it's very easy to go along with. So its capabilities are style transfer, activity classification. So this is, as I mentioned before, if you want to be able to take sensor data and classify that your user is doing, let's say like rock climbing or windsurfing or yoga, you can classify these and they can actually go well outside the realm of what Apple offers already. It can also do image similarity, recommendations, and object detection. So although this is in Python, it exports as an ML model, so you're able to use CoreML with this right after you finish training. You don't have to go through any conversion tools. So setting up the Python environment can sometimes be a pain point for people. So instead of using your system installation, it's recommended to use a virtual environment or Anaconda or something like this. So I chose to use virtual env, and so to set it up, you just create a virtual env, and then you activate it, and then you use pip, which is the Python package manager, to install the requirements that you need in order to run Turi Create. So we're running the beta version of Turi Create, which is like newer, and so it allows us to do style transfer, because this is an addition that was just added during WWDC 2018. We also need to install Jupyter, which is for a Jupyter notebook, which is sort of similar to a Xcode playground, but it runs in the browser, and we're going to use this to go through the style transfer example. And then it also needs this requests dependency, which I found out just from the debug output when I tried to install just these two. So to kick off the training for this, we want to launch the Jupyter notebook. We just do this in your terminal. So I'm going to show you what this looks like in the browser. Let me just mirror. Can everyone see that? Okay. Okay, so yeah, basically you can see the code that you need to execute, and you can run these line by line, and you can also have inline markdown. So it's nice to just go through, and actually it looks like a notebook, because it looks like you're like annotating what you're going to do next. So first we need to import Turi Create, and then the next thing we're going to do is load the style and content images. So instead of having a training and test set like we did for the image classification, we're going to have this style data set and this content data set. So the style is going to be a set of images of the artistic style that you want to transfer. So this is where you can add like Dali paintings or Van Gogh paintings, or even your own paintings if you're an artist. And then the content's going to be sample content that you would expect. So this isn't necessary to get 100% correct, because you might end up using this in a lot of scenarios, but it just helps the model. If you know that you're going to just take photographs of city streets and send them through style transfer, then try to provide a content data set that has photos of city streets. Similarly, if you just think you're going to do selfies or landscapes. So basically, you just call Turi Create load images with each of the style and content paths. And then this is actually, you can ignore this unsupported image format. It actually does work. And then next you're going to train the model. So you're calling Turi Create to a style transfer, so to the style transfer module, and then the create method. And you're going to pass in the style and the content data set paths, and then the number of iterations. So the number of iterations by default is like, I don't remember off the top of my head, it's extremely high though. And if you try to do it with the default max iterations, it's going to take like a day or two on most laptops. So I would recommend setting this to quite a lot lower. So I was able to experiment with this, and I saw that 300 is an iteration amount, which gives you a basic style transfer. It's not extremely detailed, but it still looks nice, and it takes a reasonable amount of time. So it took 3 hours on my MacBook Pro. So you can run this on like external GPUs as well. So if you're interested in doing a style transfer that's really good, you can go explore that route. So this will run for quite a while, and then when it's done, you well, you can save it if you want to try to use this later on in the browser, but that's an optional step, actually. The next thing you want to do is you want to load test images so you can see how the style transfer worked. So for my example, I'll go back to it in the slide deck, but I did the style transfer of the photo that I showed at the beginning of the presentation. And then next you're going to be stylizing the test images, and you can also explore. So yeah, basically there's an interactive exploration module. I would have to run through all of these lines though in order to activate it, and we cannot go through 3 hours of training right now in order to do that. So after you're done with that, you need to export the model. So this will go directly into ML model format, and yeah, from there you'll be able to use it with CoreML. So even though it's in Python, it's just maybe a dozen lines of code, and I think it's pretty easy to run through with very little Python knowledge. Okay, so yeah, with that, the tour de Apple ML is over, and I hope you learned some, and I hope you feel empowered to include machine learning in your apps, and you will get started with these frameworks if you feel like it's something that your apps could benefit from. Thank you. I think we have time for some questions.
Hi, can I transfer TensorFlow model to CoreML?
Yes, you can transfer TensorFlow models to CoreML. So I covered just tools that are within the Apple ecosystem, but for TensorFlow, you can use a tool, I forget the exact name of it, but it is officially endorsed by both Google and Apple. And it's similar to CoreML tools, if you've done that before, which is the conversion from Caffe and Keras and a lot of other providers. TensorFlow has a very similar tool, but it's just called something else other than CoreML tools. I can post it in the Slack, actually, after this.
Okay, thank you.
Any other questions?
Thank you for your interesting presentation, and at the beginning, I would like to point that I'm not a CoreML expert at all, but I would like to ask you the question about the set of images. You divided it into two sections, training and test, in the ratio 8:2. And some people are dividing these sets into 3 parts, which is testing, validation, which is training, validation, and testing. What's the purpose for validation?
Mm-hmm. Yeah, it's a really good question. So under the hood, CreateML does divide your set into training, validation, and test. So you provide it with the training set and the test set, and it takes your training set and allocates 5% of that to validation. And validation is similar to a test set because it's separate from what the training process is using in order to train the model and improve it. But it's used in order to take input during the training process. So it's kind of like as you go along, a check to make sure that it's being trained and is improving in the right direction. Whereas your test data set is not touched at all until after you decide that you're done with the training process, at least like for that set of iterations. And then you would go and use the test set in order to evaluate it. Does that make sense?
Yes, that's a great explanation. And one more question, can you present some output of the last part of the presentation, like some transformation from the actual image to some artwork?
Yes, yeah, I can actually show you right now.
Okay.
Very good point. I actually said I was going to do that.
Yeah, that's really nice.
Yeah, this is the transfer that I was able to get with the 3 hours of training. If you train this for longer, you would have a much more detailed transfer.
Thank you very much.
Thank you. I actually can't tell if anyone's raising their hand, so I guess I'll just wait and see. So bright. Doesn't seem like there are any other questions. Okay, thank you very much for coming, and I'll post my slides as well as the TensorFlow converter and any other resources that I think would be useful in the Slack channel.